Hello, everyone. In this Chapter 2 lecture, which should be a really fun lecture, I'm hoping, we're going to be taking a look at elements, how we describe elements in a variety of different ways, as well as the arrangement of the elements on the periodic table. So we've already met elements in previous lectures, and of course you've taken chemistry before. And one of the things you should already know about elements is that they are pure substances. In fact, they are the simplest type of pure substance. This is because when you take an element, it is impossible to break that element down into any simpler substance using chemical processes. Okay. So that's one thing we already know about elements. Something else we already know about elements from our last lecture in particular is that the atoms of a given element all contain the same number of protons. So for example, if we have a sample of sodium, we know that all sodium atoms contain, well, how many protons do they contain? They all contain 11 protons. Now, we also know that the number of protons in one element, are different from the number of protons in another element. So this number is unique for every element. So if we're talking instead about, say, the element iodine, well, all iodine atoms contain, well, how many protons do they contain? They contain 53 protons. Nitrogen atoms contain 7 protons. Manganese atoms contain 25 protons, so on and so forth. You may also remember from our last lecture that the number of protons is obtained from the periodic table for each element in the form of the atomic number Z. But we'll review that a little bit later. But that was from the last lecture. Now, as it turns out, all known elements are found on probably the most important tool of a chemist, the periodic table of elements, And they're organized into rows and columns of varying lengths. Turns out that the periodic table was first developed by a Russian chemist named Dmitry Mendeleev in 1869. And back in 1869, many of these elements had not been isolated or discovered yet, and he actually left blank spots in his designed periodic table, all right, for those missing elements. It was quite amazing. So some of you may recall that a row of elements on the periodic table is called a period. Okay, rows, of course, go across, left to right, left to right, left to right. Some rows, some periods only have 2 elements. Period 1 only has 2 elements in it, hydrogen and helium. Period 2 and 3 have 8 elements in them. 1, 2, 3, 4, 5, 6, 7, 8. Period 4 has an additional 10 elements in it. So 8 plus 10, 18. So there are different numbers of elements in each period. We designate each period by numbering them. 1, 2, 3, 4, 5, 6, 7. Let's write that now down, that these periods are numbered 1 to 7. Okay. But wait a minute, what about these last 2 rows at the bottom of the periodic table? Well, these last 2 rows here, which are separate from the rest of the periodic table, are not periods 8 and 9. That's not 8, this is not 9. They are named, however. The first extra row here is called the lanthanide series. Sometimes they're just called the lanthanides. And the second row is called the actinide series or the actinides. Turns out they're not numbered 8 or 9 because the lanthanides are actually part of period 6. They just don't fit very well, and so we pull them out. Likewise, the actinide series is technically a part of period 7. So I'm going to actually note that down here. So the lanthanide series is part of period 6. I'll write P6 or period 6. And the actinide series is really part of period, whoops, it should say P there, period 7. There we go. Okay. Turns out that the lanthanides and the actinides are collectively known as inner transition elements. or inner transition metals, because as it so happens, they're all metals. I'm going to write that down here. These are called the inner transition metals. That's what this collection of elements is known as. Okay, so that's our periods and our rows. Our rows are our periods. Well, what about the columns? Well, we also have columns of various lengths, and the columns of elements are known as groups. They also go by another name. Sometimes groups are known as families. So families or groups, same thing. Okay. Now, they are also designated by a numbering system, but it's a slightly different numbering system than the one we use for periods. Groups are designated by a number and a letter, where that letter is either an A or a B, number plus letter. So let's make a note of that. Designated with a number plus a letter. So, for example, 4A. I should note that on older periodic tables, the number that is put with the letter is sometimes in the form of a Roman numeral. So you should know your Roman numerals just in case you happen to end up with an older periodic table. So, for example, Roman numeral 4A. So know your Roman numerals just in case. Okay. Another thing I want to note about groups of elements is that elements in the same group tend to exhibit similar chemical properties and often to similar physical properties, but the real importance is that they exhibit these similarities in their chemical properties. So I'm just going to make a little note about that. Elements in the same group exhibit similar chemical properties. So, for example, let's take the metals in group 1A. The metals in group 1A are all highly reactive metals. They react with air. They react with water. They react with halogens in group 7A. They all show similarities in their reactivity. On the other hand, the elements in group 8A are notable for their lack of reactivity. So these are things that we're going to be exploring later on in our chapters as we find out, well, what's causing these elements to react in such similar ways. That's coming soon to a lecture near you. Okay. Now, many of the groups of elements are not only designated with a number and a letter, they're also given a particular name. And some of these names you learned in Chem 10. So, for example, you might recall that the elements in group 8A, here, let's do a color coding to match the diagram. So the elements in yellow in group 8A are known as the noble gases. Meanwhile, the elements in group 7A, which, let's see, it's a sort of orange color. Oops, I got an orange color right here. In group 7A, you might recall these are called the halogens. In group 6A, this is a name that students are much less familiar with. Let's see, I need a gray color for group 6A. There we go. The elements in group 6A commonly go by the name of chalcogens. The CH is a hard CH, chalcogens. And that would be the elements oxygen, sulfur, selenium, tellurium, polonium. They're known as the chalcogens. Now, over in group 2A, not all of the groups of elements have special names. So we're just going to point out the more important ones. In group 2A, we're now dealing with a group of metals commonly known as the alkaline earth metals. Alkaline earth metals. And bringing up the rear are the elements in group 1A, with the exception of hydrogen. So hydrogen is in group 1A, as you can see, but ignoring hydrogen, the rest of those elements are known as the alkali metals. Now, something else that's important to note are whether the designated letter in a group is an A or a B. So we have 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. If the group is designated by the letter A, we say it is a main group element. So let's write that. Number and A. Number and A. Do I have a red color that I can use to highlight this? I don't think so. So let's just write this. Equals a main group element. However, if the group is designated with the letter B, 3B, 4B, 5B, so on and so forth over here in this green section, well, the number plus the B indicates that we're dealing with a transition metal. Transition metal. Here, we have a green here, equals transition metal. And I'll even highlight that in green so it sort of color codes with everything else that we have so far. There we go. Transition metals over there in the B section of the periodic table. So I think you've learned all of this before. Nothing is really new here. We're just reviewing this and getting you up to date and up to speed going from Chem 10 to Chem 11. Now, each element is in a box on the periodic table. And typically we call these little boxes cells, each cell. So it turns out each cell on the periodic table supplies certain information about that particular element in the cell. Now, some periodic tables will give you a tremendous amount of information about an element, all right, on the periodic table. Sometimes a cell will tell you things like its density, its electron configuration, all sorts of information. But at the very minimum, you can be assured to be provided with 3 key pieces of information. So let's, for example, take the element carbon. Okay. Well, the key pieces of information you should find on every periodic table are the element symbol, the element's atomic number, and the element's atomic mass. Okay, so let's label this here. So here we have the element symbol, where the element symbol is always going to be based on its name. Now, some periodic tables will give you both the symbol and the name. And the periodic table in your textbook, and there's periodic tables in multiple locations in your textbook, will do this. But this one obviously doesn't have that. But again, we're talking about the basic minimal information you can get from every periodic table. We've already met the number that is always in the top of a cell. This, of course, is the atomic number of the element, aka letter Z, and we already know that this is equal to the number of protons in an atom or an ion of that element. This number will always be at the top. It could be in the top middle, top left, top right. It'll always be at the top, and it will always be a whole number. Turns out that number is an exact number. Why? Because we count protons. 1 proton, 2 proton, 3 protons. So it's an exact value. Now, the number at the bottom, which again could be towards the left, right, or center, is known as the atomic mass of the element. Let's write this here. The atomic mass of the element is not the same thing as the mass number of an element. In our last lecture, we talked about mass number. Mass number is the number of protons plus the number of neutrons given by the symbol A. Atomic mass is different. Atomic mass is the average mass of an atom of that element in units of AMU. So this is the average mass of an atom of the element in atomic mass units. We're going to talk a lot more about atomic mass when we get to chapter 3. Now, one more little thing about this number here, atomic mass. On some periodic tables, the atomic mass will be given more precisely than on other periodic tables. What does this mean? It means on some periodic tables, there'll be more decimal places. So don't freak out if some periodic tables give you more or less. It's just a function of whoever designed that periodic table and what they decided to do. I would never use a periodic table, however, that gives you less than 2 decimal places. You should have at least 2 decimal places for those atomic mass values. Okay, so moving on. It is really important to start memorizing names and symbols. Yes, I know that in this online course, it is open notes, open textbook when you take exams, but you really can't be wasting time looking up the symbol for tin or antimony or anything else on the periodic table because you're losing time on exams. So do start memorizing names and symbols. What should you know the symbols and names of inside out? Well, really, I think at minimum, you should know the names and symbols of all main group elements. So let's remember that the main group elements are the ones with the A's. So that would be those in group 1A to group 8A. Okay. In addition to all the main group elements, you really also should memorize all of the transition metals in period 4. So transition metals, and so I'm going to put comma over here, transition metals in period 4. And in addition to the transition metals in period 4, are just a few extras, so I'll say plus. The extra ones that you should memorize as well are silver, cadmium, gold, and mercury. So these are elements that are going to come up again and again and again and again. So absolutely, it would be a good idea if you had them memorized. Okay. Now, you should also, of course, pay special attention to any elements that have symbols based on Latin names. So typically, the symbol of an element corresponds to its English name. So the first element on the periodic table that begins with C is carbon. So carbon is C. But it's not the only element beginning with the letter C. All right, later on we have chlorine. Chlorine is Cl. Okay. Later on we have calcium. Calcium is Ca. Cobalt is Co, so on and so forth. Please note that the first letter in a symbol is capitalized. The second letter is lowercase. So please, please, please get that right at this point in time. You cannot write chlorine as capital C, capital L. That is just not correct. Anyhow, getting back to the Latin names. Every now and then we come across a symbol that doesn't match its English name. Let's take sodium. Sodium is Na. Now that seems kind of strange. Why isn't sodium S or SO? Well, it's because sodium symbol Na comes from its earlier Latin name. And that Latin name is natrium. And so let's just write out those elements in particular. So those elements are sodium, potassium, okay, iron, copper. What else do we have? Silver and gold. We also have mercury and lead, antimony, and tin. So these are the elements that have symbols based on Latin names. I'm actually going to write out the Latin names for 5 of these elements, and I'm going to make this a little bit clearer. This is copper, which is Cu. There we go, Cu. So I'm going to actually write out the Latin names for some of these because they're going to become important for you to know when we do nomenclature of ionic compounds in a soon-to-come lecture. So iron, Fe, gets its symbol Fe from its Latin name, which is ferrum. Copper, which is Cu and not Co, comes from the Latin word cuprum. Gold, Au, comes from the Latin word aurum. Lead comes from the Latin word plumbum. And tin comes from the Latin word stannum. Okay. Plumbum actually also gives its name to an entire occupation, plumbers. Plumbers are called plumbers. It's a word based on the Latin word for lead because they originally worked with lead pipes. Okay. There is one other element that has a symbol that does not agree with its English name, and that is wolfram. Wolfram, which has the symbol W. Sorry, Wolfram is its original name, so I take that back. All right, its English name, of course, is tungsten. Tungsten. So tungsten comes from a Scandinavian name. So it's not Latin, it's Scandinavian, Wolfram. Wolfram actually corresponds to the English translation heavy metal, and it is incredibly heavy. Tungsten has a crazy high density, making it a very, very, very heavy element. So I'll put that in brackets off to the side because it's not really based on a Latin name. Now, we've taken a look at the organization of the elements on the periodic table. Well, we also need to be able to accurately describe the elements on the periodic table. And in particular, there are 3 things we need to be able to describe about the elements. First, we want to be able to say what their physical states are at, well, RT stands for room temperature and pressure. Room temperature and pressure. Room temperature is typically defined as 25 degrees Celsius and room pressure 1 atmosphere. So what is their naturally occurring physical state? Okay. Well, if we take a look at this periodic table supplied here, the physical states are indicated by the color of the element symbol. So in most cases, the element symbol is black, like this carbon symbol is black, this iron symbol is black. But in some cases, the element symbols are red. Hydrogen's element symbol is red. Argon's element symbol is red. And a very small number of element symbols are shown in deep blue, bromine and mercury. Well, this is to indicate that the elements occur naturally in different physical states. So let's start there. So if we look at the element symbol, oops, that should be an L over here, element symbol. Okay, if the element symbol is black, well, that element occurs naturally as a solid. If the element symbol is shown in that deep blue, that element occurs naturally as a liquid. And if the element symbol is shown, oops, in the color red, well, that element is naturally occurring as a gas. Okay? And if we look at this periodic table, here, let me scroll down a little bit here. Well, what do we see? Well, we see that there are only 2 naturally occurring liquids at room temperature and pressure, and those are mercury, which everybody should be familiar with, and the element bromine, which is one of our halogens. Mercury and bromine, only 2 liquids. Okay. Meanwhile, there are only 11 naturally occurring gases. Those gases include all of the group 8A noble gases, helium, neon, argon, krypton, xenon, and radon. In addition to the noble gases, we also have hydrogen gas, nitrogen and oxygen, which everybody should know since they're both major components of air, as well as 2 of the halogens. Fluorine is a gas and chlorine is a gas. But not bromine, that's a liquid. Not iodine either. Iodine has got a symbol in black. It's a solid, as is astatine. So most of the elements, seeing that their symbols are written in black, occur naturally in the solid state. Okay. Now, another thing I want to bring your attention to is some of the element symbols have a little asterisk or star beside them. In fact, I'm going to use a little highlighter to show the stars. So here we have it for hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and astatine. Well, the little star beside the element symbol indicates that these elements naturally occur as diatomic molecules. So I'm also going to write that over here. I'm going to put a little star here. I'm going to make it bright, a little bright star. And let's note that these elements are diatomic. Diatomic elements. Now, being composed of diatomic molecules means that the atoms of these elements are bonded to themselves, two atoms bonded together. And therefore, when we write the formulas of these diatomic elements, we have to include the subscript 2. So it is H2, N2, O2. Let's just write them all out. F2, Cl2, Br2, I2, and At2. Diatomic elements. Okay, did I leave any out? Looks like I got them all. So again, when we write the formulas of diatomic elements, we include 2 in the subscript. So we are able to describe which elements are solids, liquids, and gases naturally, and which elements occur naturally as diatomic species. Well, the third thing that we want to be able to do is to describe what is called the character of an element, and that is whether that element could be described as a metal or a nonmetal or a metalloid. And it turns out what's going to help us with that is the presence in most periodic tables, not all but most, of a very heavy, some people call this the staircase line. I like to call it the zigzag line, the zigzag line. So always look out for the zigzag line. And as it turns out, if an element is to the left of the zigzag line, well, left of the zigzag line, we're working with metals. So metals are left of the zigzag line. So let's highlight the word metals to color code it. Let's put this. That color doesn't quite match the color that's on the video. So let's see if I can make the color match. Let's mix 2 colors together. Oh yes, that's much better match. Would you not say so? There we go. So metals are sort of this melony color on the periodic table. They're left of the zigzag line with one notable exception over here, hydrogen. Hydrogen is left of the zigzag line, far left, but it is not a metal. It is notably a non-metal. So let's also note non-metals, with the exception of hydrogen, are to the right of the zigzag line. And I'll just say except hydrogen, which is not quite in the right spot. And let's see if I have a color to match the nonmetals. Oh, perfect color match. How about that? Okay. And well, that leaves a few elements that are actually adjacent to the zigzag line, which are the metalloids, where the metalloids are shown in that very bright highlighter blue color. Let's see if I have the bright highlighter blue color. Perfect match over here. They are adjacent. They are adjacent to the zigzag line, which means they actually touch the zigzag line. And I apologize, my phone is ringing. Give me 1 sec as I take care of that. Okay, sorry about that. Okay, so let's just look a little bit more closely at the metalloids. Again, adjacent means they touch the zigzag line. Not all the elements that are touching the zigzag line are classified as metalloids. The metalloids are boron, silicon, germanium, arsenic, antimony, and tellurium. The elements that are touching the zigzag line that are not metalloids include aluminum, which is a true metal, as well as polonium, a true metal, and on the other side of polonium, astatine, which is a true nonmetal. but most of those that touch the zigzag line are in fact metalloids. Okay. Now, one of the things we should discuss are some basic differences between metals, nonmetals, and metalloids. If we are classifying them differently, they must somehow behave differently and show different properties. So what are some of the key properties of metals, nonmetals, and metalloids? Well, I'm just going to scroll down here to this little bit of empty space, and let's take a look at some key characteristics of the element's character. So let's start with metals. Well, one important thing the metals have in common is that with the exception of mercury, all the metals occur naturally as solids. So I'm going to say most are solids at room temperature and pressure. Okay. Something else about most of our our metals, is that they appear shiny or they have luster. So they're shiny, they have luster. Okay. Metals are quite useful because they can be reshaped. And the word that we use to describe this ability to be reshaped is we say that metals are malleable and ductile. Ductile means that the metals can be drawn into thin wires, Okay. Well, what else can we say about metals? Well, we also know that metals are good conductors. They're good conductors of both heat and electricity. So, good conductors of heat and electricity. Now, in contrast, when we look at our nonmetals, well, nonmetals show a lot more variations in their physical states at room temperature and pressure. If we look at the collection of nonmetals, we see that some are solids, some are liquids, and some are gases at room temperature and pressure. So, some are solids, some are liquids, and some are gases at room temperature and pressure. Now, if we look at the solids amongst our nonmetals, what we're going to find out is they are most definitely not malleable and ductile. If you take a metal and you drop it on the ground, all right, it'll deform, it'll dent. But if you take a solid nonmetal and drop it on the ground, it shatters into pieces. So we say that the solid nonmetals are, the word we like to use is brittle. They are brittle. And all nonmetals, regardless of their physical state, are not good conductors. They are poor conductors. They are poor conductors of both heat and electricity, and they're often described as being insulators. That's the word we use for substances that are poor conductors of heat and electricity. Well, what about our metalloids? Well, as it turns out, metalloids are rather like the in-between character, just as liquids sort of are the in-between state. So metalloids, as it turns out, exhibit properties of both metals and nonmetals. So these exhibit properties of both metals and nonmetals. And I think one of the best ways to illustrate that is with an example. So the quintessential example of a metalloid is silicon. If we were to describe silicon, the most basic description of silicon, well, silicon is a solid, and it's actually quite shiny. It's quite beautifully shiny, which is typically a property of metals. Now, even though it's this beautiful shiny material, if you were to drop a piece of silicon on the ground, it would shatter into lots of pieces, which means it's brittle like a nonmetal. So let's note it is a shiny, brittle solid. Well, what about its conductivity? Well, it's certainly not a good conductor like a metal, neither is it a poor conductor or an insulator like a nonmetal. All right, turns out silicon displays conductivity properties in between metals and nonmetals, which is why we call it a semiconductor. Hey, how about that? So let's also note that it is a semiconductor. And of course, these are things that you're going to be exploring. Why are metals good conductors, nonmetals poor conductors? Why does a metalloid like silicon a semiconductor? What does that mean? That's all for a future lecture. Future lecture, not even one by me in this class. That's going to be a Chem 12 issue. But don't worry, you'll get there. You'll get there eventually. I should note that the properties I've listed here for metals, nonmetals, and metalloids could best be described as physical properties. These are physical properties metals have in common, nonmetals have in common, metalloids have in common. Are there any important chemical properties I should mention? Well, just a couple. Let's just note that metals tend to lose electrons and form cations. So they readily form positively charged cations if prompted. Whereas nonmetals are going to be observed to do the opposite. Nonmetals readily form anions. And let's remember, anions are negative. This is true of all our nonmetals, save one group of nonmetals. All right, the exception being the noble gases. So, except group 8A. They don't readily form anions, or cations for that matter. Metalloids don't generally form ions. They can form ions, but it's not their preferred mode of reactivity. We'll find out what they like to do later on. I'm also going to note that metals will readily chemically react with nonmetals. And when metals chemically react with nonmetals, they form ionic compounds. So I'm just going to use M for metals. So metals react with, I'm going to use NM for nonmetals, forming ionic compounds. But metals don't chemically react with other metals. They don't do that. Now, as for nonmetals, well, if metals react with nonmetals, nonmetals are clearly reacting with metals, forming ionic compounds. So do nonmetals chemically react with other nonmetals? Well, the answer is yes, they do. And when nonmetals react with other nonmetals, the result is the formation of covalent compounds. So nonmetals react with other nonmetals, forming covalent compounds. Okay, so now we've done a quick and fun, hopefully fun, review of elements and the periodic table. Up next, a review of compounds, and we're saving the best, I don't know if it's the best for last, but we're going to be doing nomenclature of all types of compounds at the very end of this particular chapter. Okay, so until then, I will be talking to you later. Bye now.